Oftentimes, in math, we are given a function, one where it takes in a certain input and then generates an output, and we kind of just have to accept it for what it is. Take the sine function, for instance. When you input something into the sine function, take pi over 2, for example, what is really going on behind the scenes such that pi over 2 gets manipulated into becoming a 1? You could say, oh, well, just plot a sine function, and then look at the output value for whatever your input is. But that doesn't really answer the question, because then you have to ask where the sine wave came from. To find out what the inner workings of these different functions are actually doing, we can use the fact that they can be represented by a polynomial. Our challenge then comes from trying to find the coefficients in this polynomial. Let's go back to our example of the sine function. To solve for a, we can start by plugging in 0 for x. All of the other terms besides a in this polynomial will be multiplied by 0, so in the end we're just left with a equals 0. The next terms in this polynomial are here to make sure that the polynomial curves at the same rate as the sine function. To account for this, we're going to take the derivative of our function, because that is the same as finding the slope of the tangent line at a given point, which will ensure that our polynomial does indeed have the same curve. Similar to what we did to the first term, we're going to plug in 0 into this new function to help us find the second term. Doing this tells us that b is equal to 1. We can continue to repeat this process of taking the derivative of our function and then plugging it into 0 to find all of the coefficients in our polynomial, and a pattern soon emerges. It seems that every other coefficient in our polynomial is equal to 0. All of the other terms, however, follow a pattern of 1 over the factorial of the exponent. Additionally, these coefficients also alternate between being positive and negative. Alright, great. So now that we have a repeating pattern, let's see if we can solve the sine function once and for all. To start, let's represent this infinite polynomial as an infinite sum. Since the coefficient of every other term is 0, we only care about the terms with odd exponents, which we can represent as x to the power of 2n plus 1. All of the coefficients of these terms are just 1 over the factorial of the exponent, which we can represent as the factorial of 2n plus 1. And finally, to account for the alternations between positive and negative coefficients, we will multiply it by -1 to the nth power. This works because even values of n will always return a positive 1, while odd values of n will always return a negative 1. And just like that, we've done it. We've officially constructed an actual definition of the sine function, where you can apply this infinite sum to any input, and it will output the sine value of that input. What we've just created is called a Taylor series, an infinite sum of terms used to represent a function. Taylor series are actually quite useful, because they can also be used to approximate a function with a partial sum of terms, rather than an infinite polynomial. This comes up in a lot of areas like physics, where finding an exact answer isn't always required.